the result going to be every time?
0.
It's going to be 0 because you'll start out with dx, dy, dz. Then when you differentiate whatever function you have, then you're going to have a dx, dy, and dz. All of them will be multiplied with this dx, dy, dz. You're going to get 2 of them, 2 of one variable in every case. They'll all be gone. So when we're talking about functions of 3 variables at the most, there's no point in working with a differentiating a 3 form. It's always going to be 0. If you extend the number of variables and allow for more basic 1 forms like dx, dy, dz, dw, then the 3 forms of differentiation operation has some meaning. Okay. Okay. So questions about this differentiation operation. Differentiate the function with respect to whatever variables are not included in here. So since we have a few minutes, I'll quickly do another. So suppose that I have form eta, that's sine x plus y plus z, and then we just have dx. So it's just a 1 form. So then the shortcut would be d eta is going to be derivative of this with respect to y, which will just turn out to be this, dy dx plus derivative with respect to z dz dx. So we have d dz here, d dy here. I guess a bad example because the derivative with respect to any of the 3 variables is going to be the same no matter what. I'll change the numbers a little bit. X plus 2y plus 3z. So at least here we'll get a 2 in this case, and a 3 in this case, so there's some difference. And then you perform any interchanges you want to get it in the standard form. So it's going to end up being minus 2 cosine x plus 2y plus 3z dx dy, and then these are already in the right order. 3 cosine x plus 2y plus 3z dz dx. So here we already have a dx, so we just differentiate in respect to y and z, and then the results of those we have the dx tacked on the end. And then if you want to do any flippings to get all your basic 1 forms in the standard order, like dx dy, dz dx, or dy dz, then you can go ahead and do that, and that may introduce some sign changes. Okay. So what we're going to find is, if we're taking a 1 form and we're integrating over, okay, so 1 form integrating over a curve, a closed curve, what we'll find is if we take the 1 form and differentiate it using this operation, then integrating that 1 form over that closed curve is the same as integrating the derivative of that 1 form, which is a 2 form, over the region it contains. So that we get a very simple statement of Green's theorem, for instance. And similar things happen throughout, because if you think about integrating over a curve, what are you doing? You have your vector field, dot product with a tangent vector. Surface integral, you have the vector field, dot product with a normal vector. Very different entities here. But it turns out that this differentiation operation on 1 forms as opposed to 2 forms, however, whatever order of form you're dealing with, it all works out exactly the same way. So so integral of a k form over a k-dimensional object is equal to the integral of the derivative of form over the interior of that object, whatever that interior happens to mean. So whatever the context, that's just how it works out. And differential forms notation that makes it happen. So on Thursday, we'll see how that happens for all 5 theorems. and we get the same result in all cases. So, all right, so one more lecture to suffer through.